I want to say. This formula that we just got, let's go back to the two-dimensional real quick. Okay, that formula. When we started the idea of partial derivatives, we did the partial with respect to x first, right? Which meant that we were going to hold y to be constant. So here's my stuff here. If I hold y to be constant, I'm cutting through the plane like this. What direction am I pointing in? What is a unit vector that points in that direction on the ground? So if I hold, this is looking from the top, if I hold my y to be constant, hold it to be a constant, then I'm cutting through the plane like this, right? Like that. And I'm standing here, then I'm either pointed in that direction or in that direction, right? One of these two directions. What unit vector could we have that points in either that direction or that direction? I, right? I hat, or that vector right there, the vector 1, 0, right? Wouldn't that be? So if I wanted the partial of f with respect to x, I hold y constant, and it's basically that vector. Yeah? What happens if you take that vector and you use that formula? Well, a is what? 1, and what's b? 0. If that's 1 and that's 0, what do you get? The partial with respect to x. Which is, I mean, that's what I'm saying. This is a generalization. When we cut through with a plane holding y to be constant, we were basically using that formula with that vector. And then when we hold x to be constant, now we're using this vector, 0, 1. And now in this formula, that kills this and keeps this one alive. So you get the partial with respect to y. Do you see how that's just a this is a generalization, but it lets us point in any direction, which is really cool. All right, we haven't gotten to the most profound part of this. Let's get to it. I think I'm going to skip this part unless y'all really want to see it. I just said that this all extends into higher dimensions. Would y'all like me to get the gradient of that? You know what, I'm thinking about it now. Have we done a partial derivative with 3 variables? Not enough of them. Let me do just at least the beginning of this. All right, there's a function of 3 variables, and I want the gradient vector. So I want del f. Del f would be the partial of that with respect to x, partial of that with respect to y, partial of that with respect to z. That, by definition, is the gradient vector. I'm going to do my partials over here. Partial with respect to x. All right, when I look at this, if I'm doing the partial with respect to x, what am I holding constant here? Y and z. So if I'm holding y and z constant up there, then I think this is the way I'm going to look at it. Okay, I'm looking at just this right now. If I look at my original function, right, f, I'm going to write it like this. If y and z are constants, then I can look at that as like a number I could pull out in front, like this. And then the derivative of that with respect to x would just be 1 over y plus z. Now, if I want the derivative with respect to y, unfortunately I can't do the same thing because the y is down in the denominator and you can't peel that z off easily. So I have options. You could, one, use a quotient rule, or you could bring the y plus z to the top as y plus z to the -1 and then do a derivative. What do you all want to do? Quotient rule or bring it up as something to the -1? -1, quotient rule? Everyone wants -1? Okay, so to do this, what I'm doing is I'm going to rewrite f this way. X and then y plus z, I'm bringing it up to -1. That's the original function rewritten so I can better take the derivative of it. Just like here, I rewrote the original function in a way that I could isolate the x and do a quick, easy derivative. So if I take this partial, x is a constant, right? Comes for the ride. Times. Now I have to do chain rule, right? I'm ignoring that chain rule here. Negative 1 comes out. Let me put the negative in front of the x. Then I have y plus z to the negative 2, right? That's the first thing, right? I have to do this negative 1 comes out, then all of this to the negative 2. And then I take the derivative inside with respect to y. What's the derivative of this with respect to y?
1.
Just 1, right? Derivative of y is 1, derivative of z is 0, because z is a constant. So that's our derivative, right? That's it right there. We have 2 of them. Any questions? Third one's going to work almost the same, isn't it? If I want the partial of f with respect to z, I'm going to look at f the same way I looked at it here. F is x and then y plus z to the negative 1. So if I do the derivative again with respect to z, x is a constant, comes for the ride. I bring the negative 1 out, so I'm going to put the negative in front of the x. And then I have y plus z to the negative 2. And then I take derivative of what's inside with respect to z. That means the derivative of that's 0 and derivative of that's 1. So I get the same exact thing, right? They're exactly the same. So the answer to this first part of this question is a vector that has as its components this, this, and this. Okay, just put those in angle brackets and you've got your answer. Part B says to find the directional derivative at the point 4, 1, 1 in the direction of the vector u equals 1, 2, 3. So now I've given you an x, y, z, right? X, y, z. And I've given you a vector. So we're just going to use the formula? Yeah. We use formula? What? Unit vector. Needs to be a unit vector. You've got to make sure that's a unit vector, which it's not. So you have to scale it and do I continue or let you do that? What do you want? You okay? Y'all all right? You understand what I need to do, right? Okay, I'm going to move on. All right.
Should we?
Yes?
Should we mark our gradient vector as a vector with the arrow?
No, you don't have to. The del is enough. Good question. The del is enough. Yeah, when you write del f, that means it's a vector. All right, so look, the big question here is if you go, let's go back to the two variables, all right? The surface in three-dimensional space. If I have a surface and I go to some point, I go out x, I go y, and I'm up here on the surface, wouldn't it be nice if it was easy to tell somebody what direction to point so that when they take that step, it's the maximum ascent that they're going to get? In other words, if it was easy for me to be able to just be on a surface and somehow just come up with this direction, that if I go that way, it's steeper than any other direction I could ever point in standing at that point. I mean, it seems like you would have to compare that to every other direction you point in, right? You understand? Is there a way to maximize this directional derivative, to find out what direction we point in to get the maximum directional derivative? And this is the big, like, holy shit, is it not as bad as it sounds? And it goes back to this idea of the dot product. See, we've already established that right there, that the directional derivative of a function is just del f dotted with the unit vector, right? Like, that's just a clever way of us writing it in notation, right? But because of this definition, if we want to figure out when does this have a maximum value, right? When is that the biggest it can be, then I want to know when that's as big as it can be, right? But if you look back at dot products way back in the day, we had a formula for dot products that said the dot product is always equal to the magnitude of the u vector times the magnitude of the v vector times cosine of the angle between the vectors. Right? So you have two vectors. If you dot them, you take the magnitude of one times the magnitude of the other times cosine of the angle between them. That's a formula from, I don't even know, chapter 10 somewhere. If we use that formula on our dot product over here, right, then we get this down on the bottom. I'm not going to reveal the rest yet. Can you all see that? Del F dotted with U is the magnitude of del F times the magnitude of U times cosine of the angle between them. And then on the next line, or next part I write, that's just del F cosine theta. Why? Because that's a unit vector. So the length of it is 1. So what we're saying is that this right here could just be written as the magnitude of the del F, right, times cosine of theta, right? That's basically what I'm saying. Now the question is, when is this the biggest it can be? Yes? When cosine is 1. When this thing turns out to be 1, that's the biggest this will ever be, right? Cosine is bounded between -1 and 1, right? So the biggest this could ever get is when that is 1, right? Which means that the angle theta must be what? What is the angle? Cosine of what gives you 1? 0. And 180, yes. Okay, so let's back up. The definition of the dot product between two vectors is the magnitude of the first times the magnitude of the second times cosine of the angle, what? The angle between the two vectors. What are we dotting together? The gradient vector, right? And the, yes, but what does this vector represent? The direction I'm pointing. And what this says is that in order to make this as big as possible, the angle between where you're pointing and the gradient vector has to be 0, which means you need to be pointing in the direction of the gradient vector. Right? Like, look, I'm standing on surface and I'm like, which way do I point to go the steepest? And this is telling us, well, you have a gradient vector, right? You can compute the gradient vector. We just did it on a couple of examples. It says point in that direction, and that's your steepest descent. Because you need the direction you point, the angle between the direction you point and the gradient vector, you need that to be 0 to maximize this. I mean, I'm sorry, but to me that's just like, whoa. Like that, it shouldn't be that easy. It shouldn't be that easy. So this is the conclusion of that. The maximum value of the directional derivative is the magnitude of the gradient vector, and it occurs when we point in the direction of the gradient vector. So we're going to do an example. Yes, sir.
So is that the primary relevance of the gradient vector?
Well, we have this, and then we can extend it to a lot of different things. It's not the only thing, but at this juncture of where we are in calculus, this is the big result. But as we're going to see, we're going to use it a lot for different things. Yeah.
So it comes up for lots of stuff.
Mm-hmm. All right. So we have this surface, right? Yes. That would be, yeah, so that's a great question. So the direction of the gradient vector tells you where you have the steepest ascent, right? You would be going like up, right? And if we just point the other way, 180 degrees, then we would have the steepest descent, right? That makes sense, right? Because if that way is going up as fast as I can, that way should be going down instantaneously at that point. Yes?
And so orthogonal to that would be the contour line where it's like 0.
Well, so you're saying if we have the gradient vector, right? Let's say here's my point, and that's the steepest descent. You're saying orthogonal to that would be the contour, right? Is that what you're saying? There's an infinite number of orthogonals, right? So it's a special one. It would have to be. There's a special. We need some other condition, or else we can't isolate which of these it is. Does that make sense?
Yeah.
Okay. But one of those is, yes, in the direction of like a contour line. All right, let's do it, right? Here we go. Here's a function of surface. Find, first of all, the direction as an angle of the maximum rate of change at the point 0, 0. So you've got this surface. We're standing at the origin. We get plugged into the function. We're somewhere on that surface. We're standing there, hovering around. And what I want to know is, as an angle, which way should I point so that when I walk out, I get the steepest descent? Well, what do you think? What is it? Well, what direction gives me the steepest descent? The gradient vector, right? So that means I need to calculate the gradient vector at this point 0, 0. So I'm going to write this down. The direction of maximum rate of change is the direction of del F at the point 0, 0. That is the main takeaway from the previous note. If I want to know the direction of the maximum rate of change, I'm going to need to point in the direction of the gradient vector at the specific point I'm looking at. So let's start first by getting del F. So del F will be a vector. All right, it is cosine. I'm taking first the partial with respect to x, so I'm holding y to be constant. So cosine of x minus y times derivative of what's inside with respect to x, which is just 1. And then plus the derivative of cosine of x with respect to x, which is minus sine x. That is the partial of that function with respect to x. Now, I realize I'm working through these quickly, right? Like I'm assuming you can get these. If you're struggling with those, do your homework, get help, ask questions. Now, with respect to y, right? So derivative of that with respect to y would be cosine of x minus y times negative 1. Be careful there, because when you take derivative of what's inside here with respect to y, the x goes to 0, but that negative y becomes negative 1 when you take its derivative. And then you have, what about this?
That goes to 0.
0, right? That's just a constant. So that's it. That's my gradient vector. This beautiful vector will tell me what direction I need to point in. All you have to supply me now is the point you're standing at, or the x and the y that you're talking about. So the gradient vector evaluated at the point that I'm looking at, 0, 0, right, would be, okay, cosine of 0 is 1, minus, right, 0, 0, 0, that's all 0, cosine 0 is 1, sine of 0 is 0. And then over here, cosine of 0 is 1, but then multiply times negative 1, so I get negative 1. So this is the vector 1, negative 1. Sorry? Minus 0, yeah. This is a two-dimensional vector, because remember, what I was saying is, we're here on the surface. The direction is a vector on the ground that rotates with me, right? So it says the directions, we're not done, right? The directions say what? Find the direction as an angle. So now I need to find the angle that corresponds to that vector. So I'm going to draw the vector. I go to the right 1, I go down 1. And I can just look at that and tell what it is, right? So you can say negative 45 degrees. You can say positive angle if you want. It doesn't matter. 315. There's no, like, I'm going to go with the positive angle. It doesn't really matter. You could use radians. 315 degrees relative to the x-axis. Let me go back up. I think that was what I started this whole thing with. Yeah, look, this is right here. I'm going to erase, yes? This surface we're looking at that we started this whole thing with, this section, is the actual surface that we just did. This is sine of x minus y. This is sine of x minus y plus cosine x. This is the surface. I'm going to take these things out. Boom, boom, boom. Oh, no, I want the surface there. So there's my surface, okay? And what I'm going to do right now is I'm going to move myself to the origin. Let me move myself to the origin. So I want to be at 0, 0. Okay. So now there I am. You see me at the origin? I'm up there on that surface. And the question now is, if I'm right there, which way do I point so I get the maximum rate of change? And according to what we just said, it's what, negative 45 or 315 degrees. So let me rotate there. Forget, how do I have this? Pi over 2. What is negative pi over 4? I don't think I have that in here. What is a positive angle? I don't know if I go far enough here. 7 pi over 4? I only went by pi over 2s. Someone on their calculator real quick, do 7 pi divided by 4. 5.4977. So I'm going to type that in right here. 5.4977. And did it go? Yeah. Okay, right there. According to what we just found, here, let me get my x and y axis in. That's that. See, that's the vector 1, negative 1. So if I point in that direction, I should get the steepest descent. Let me bring a plane in here so you can see it. There we go. There's my, sorry, it keeps flipping on me here. So I'm pointing in that direction, and I get the steepest descent. I don't know why you can't see the values. I have the computer calculating the values here, but I'm not sure why you can't see it. So I'm going to try and, maybe if I make it a little smaller? Oh, no, it's still not showing it. What the hell? Make this, maybe if I make this smaller. There we go. Okay. All right. So according to the computer's calculation, this is the rate of change in that direction, right? That's the rate of change. 1.41 something. Looks like the square root of 2, doesn't it? If I rotate it all right now, what should I expect that number to do? Get smaller, right? So I'm going to do it just to verify it. I'm going to rotate myself a little bit and just watch the number. This thing got there. I got it. So I rotate a little bit. See, 0.9. So that's pretty cool, if you ask me. This works for any surface. Any surface. We can find, as long as we can find the gradient vector, we can find the direction we need to point in for the maximum rate of change. Okay. See where we are. We still have a little bit of time. Why don't we just make this last 10 minutes, 9 minutes? Why don't you try this one, working together, whatever. This is a function of 3 variables, so it's going to be a little bit harder to, visualize, but it's the same concept. I want you to find the directional derivative at this point, and I give you a vector. And then find the magnitude of the gradient at that point. So see if you can do those 2 things, which means you have to understand what this is asking you, right? Okay, go for it. Yes?
I do have a quick question, just conceptually make sure I understand correctly. For finding the steepest rate of change, you just find your gradient and then plug in the point, correct?
Yes. Well, that tells you the direction.
Yeah, to find the direction of.
Yeah. Oh, you know what I didn't say is how we find the actual maximum rate of change. You just take the magnitude of the gradient vector. I failed to say that. Remember how we got this vector 1, negative 1? Remember that? That's the direction we point in. But if we want to know what that slope was, we just take the magnitude of that. And if you take the magnitude of that, you get square root of 1 plus 1, which is root 2, which is why the computer was showing the 1.414 thing. Okay? I left that out, sorry. Okay? I mean, that's pretty crazy, right? The gradient vector not only tells you which way to point, but its magnitude tells you the rate of change. Nuts. All right. Look, it's 2:32. Class is over. So this is just if you want to try and work this out. You have any questions? I'll hang out. You know, if you're happy, you don't have to sit here and do this. It's not gonna. But don't leave if you don't know what this is. What you're supposed to do.